So welcome to lecture 6 of our CS2 classes. And in yesterday's lecture, does anyone remember what we studied? So we started off with something known as invariance property, which was for MLE, which says that if we have a lambda hat as the MLE for lambda, then for any transformation on the same lambda hat, so that again, that itself will be the MLE for the same transformation carried out on the lambda. And then we went on to study method of percentiles, where we looked at, how do we use the similar kind of a technique like method of moments if the distribution that we're looking at does not have moments, or the moments may not define the all of that there is to the distribution that we're looking at. So that was what we did. And then we had a look at quartiles and the median as well. And then we did an example about Weibull. Did everyone figure out the answers for this? Did everyone try?
Yes, ma'am.
And what was the answer that you got?
I had verified it yesterday itself. The gamma was 0.803777 and C was 0.002326.
Yeah. Perfect. So that is all. I guess, did anyone have any issues with solving this?
No, ma'am, but at least I am still stuck with the expected value of X of Burr and Weibull. So if you could just do it once in class.
Yeah. That we're gonna do today. Don't worry. So then we had a look at goodness of fit, and we actually kind of derived what formula should we use, and then a sort of an example where we learned about the value and what does it say and the degrees of freedom and how you figure out the degrees of freedom for the sum that you're given. And so did everyone try Weibull distributions mean? Because I've received only from 3 people. I received answers only from 3 people about the mean of Weibull distribution. So let us try to do Weibull first. Let me check. So let us try to do Weibull first, and I'm gonna do it like real quick. So if you still have any doubts, just ask me, okay, upfront. So whenever I'm talking about a mean of any particular distribution, we know that the formula to figure out its mean is integration of x, f of x, dx. So because I'm looking at a continuous distribution, I know I have to keep up with the integral. So next, I'm just going to substitute in the f of x for Weibull. And Isha, can you guide me as to what is the f of x here for Weibull distribution?
Yeah, just a second. Yeah, f of x is c times c into gamma.
Yeah.
Into x raised to gamma minus 1 into e raised to minus cx raised to gamma.
And is that it? Should I write something else here?
Dx.
Dx, right? So we are observing changes with respect to x here. So again, I will just, this is x raised to 1, so I'm just gonna make this go away and this as well go away. So it's still the same thing, right? Okay, so let us do one thing. We have to integrate with respect to x. So I know that my c and gamma are just constants. So I'll take this c and gamma outside, and what I'll have is 0 to infinity, x raised to gamma, e raised to minus c x raised to gamma dx. So what do you guys think I should do now? I want answers from, I guess Sabri and Mihil, you guys have submitted the Weibulls. And what about others? I want answers from others. What should we be doing here? What can I do next? So now I want to figure out this integration. And I know that I have something going on from 0 till infinity. So it's a definite integral. And I'm looking at changes with respect to x variable here. So I have something x raised to gamma here. And then I have e raised to minus c x raised to gamma there. So what should I be doing next? Anyone? Apart from those who have already submitted the answers. Vanshita, Anvaya, Isha, what do you guys think I should be doing here?
The integral part, we should try to get it in some form of PDF of some distribution.
Okay, so if you have a look at your formula booklet, try to see what kind of a distribution looks alike to the one that we have on the board.
Does it look like the exponential distribution with x raised to gamma equal to lambda? Like, because our exponential is lambda into e raised to minus lambda x, right?
Yeah. So again, what are you saying lambda should be?
Lambda equal to x raised to gamma.
So, okay, let us try to substitute this here. So what will I get? X raised to gamma, e raised to minus, x raised to gamma times x, right?
Yeah.
And again, lambda is the parameter here, right? So you can only compare parameters with parameters and variables with variables.
Right.
So this cannot be varying, with x varying. So lambda can never depend on x. But yeah, that's something ahead with the thought process. Anything else? What else can we have? So remember, just trying to see another distribution in the integrand that we have is not the only way to solve an integral. Sometimes it might just be easier to solve it using the normal integration method that you would have applied if there was no distribution which looked alike to the one that you have here.
So should we use substitution method for this one, like x raised to gamma as t or something?
Okay, let us try. We don't know for sure what is going to work. So let us try substitution. Do you want to try? What should I try to substitute and what for?
We can take x raised to gamma as t.
Okay. And what should I do next? Take the derivatives of both these, right? So I'll have d of x raised to gamma and d of t with respect to some d, right? And which will just in a way cancel each other out. So if I'm supposed to differentiate this guy, what I will get here is gamma times x raised to gamma minus 1, right? And I'll have dx along with it, and that will be equal to dt here, right? Does this make sense?
Yes, ma'am.
And what should I be doing next? Yeah. So what should I be doing next? Anyone would like to help us? Come on. What do we generally do when we are trying to use substitution method to solve any integration problem that we have at hand? Isha? Anvia, what do you think? Vanshita, what do you think? So again, just to remind ourselves, we did all of these. Basically, we equated this to t because we wanted to do something with this integrand right here. So whenever I'm going to write my next step, I'll just write this as it is, and I'll have 0 to infinity. So what should I be doing here or there? Anything?
So we take dx equal to dt upon lambda into x raised to lambda minus, gamma into x raised to gamma minus 1.
Perfect. And what should I write here?
T into e to the power minus ct into dt upon gamma into x raised to gamma minus 1.
And now what should I do?
We can cancel out the gammas.
Yep. Vanshita, Anvaya, can you guys follow?
Yeah.
That was a very dim yes. Anvaya?
Yeah, I can follow.
You can follow, right? Okay. Anvaya, what about you?
Yes, ma'am.
Are you there? Okay, thank you very much. So what do you guys think I should be doing next? Mihir and Savri, would you like to help your classmates? Give them a hint or something? Not the answer.
You can substitute the value of x raised to gamma minus 1 as in terms of t again.
Yeah. Is that what you guys would like to do?
But if we do that, it will be like x raised to gamma into x. X raised to gamma upon x. So again, the x will come into the picture, right?
So let us try to do something like what you just said. So I'll have x raised to gamma
Into
upon x.
Sorry, upon x.
right? Yeah, into x. I mean, if I write it in the numerator, it will be x, right? So yeah.
X raised to
Okay, and
gamma
I
will be
can
t.
x raised to gamma will be t. So if I write x raised to gamma as t, I already have a t in the numerator here.
Yeah, so it will get cancelled out.
So I can
So it
erase
will-
them both.
Yeah, so it will just be x into e raised to minus ct.
Right, it will just be x into e raised to minus ct. So now what should I be doing? Now what can I do? Can I take this x outside because I'm differentiating with respect to t? And is my x constant when I change my value of t?
That was the same thing that I was gonna ask.
Okay. So what do you think I should be doing now?
I think we
take
can
x
take
out.
X out.
We can take x out. Okay, so let us see. So again, what we are trying to see here is what will allow us to take x outside is the very fact that we are yet convinced that if you change the value of t, your value of x will not change. This is what we believe, right? Yes or no?
Yes, ma'am. Yes.
So let us have a look at what we have here. So we have something like this. Now, can you guys still say the same statement that if I change the value of t, my value of x won't change? Do you guys still agree with that fact? So I have my t, which is equal to x raised to gamma, right? So I can maybe rewrite this statement as something like x being equal to t raised to minus of gamma, right?
Yes.
Sorry, it will be 1 upon gamma, right? Or minus gamma.
1 upon gamma.
1 upon gamma.
Yeah. So what do you guys think is happening here? Can I take x outside?
No.
Why?
Because it depends on t.
Right, it depends on t. Okay, so one thing is clear, we cannot take this x outside. So what should we do now? So what else can I do?
Then do we have to convert it back in terms of x?
Do we have to convert back in terms of what?
In terms of x.
Okay, what do you mean by that? What should I write here?
I mean that wherever we have t, like, do we have to replace it again? Like, t will become x raised to gamma again. Do we have to do that?
What does Anvaya think? Vanshita, what do you think about this? So
I
Isha,
think we reached at the same place where we started.
exactly right, because what we did was we started off by replacing all of the x's we had with t's, but it turns out that there is still one x which was hiding behind. So shouldn't we try to replace this x with t itself?
Yeah, we can do that.
We can do that, right? So let us try to do that. Because anyways, at the end, what we want is an expression involving t's, right? Because we're differentiating with respect to t. So we want to see what happens to this guy if we are varying t over these integrals. So let us try to see what happens now. So I try to substitute instead of x, this t raised to 1 upon gamma. So what I'll have here is c integration from 0 till infinity, and instead of x, I'll have t raised to 1 upon gamma. And again, now I have e raised to minus ct dt. Does this look correct? Does this make sense?
But then again, how will we proceed with this ahead?
Exactly right. So there seems to be something off, and we have to try to figure out what that is. Vanshita and Vaya, what do you guys think?
I don't know, to me it looks like a gamma distribution, like kind of gamma distribution.
Kind of gamma distribution. So let us try to open our booklets. Let's see what's in there. For gamma distribution, it's on page number 12, right? So Vanshita, can you guide me through comparing this gamma distribution and this integral right here? Maybe we can,
Lambda would be t. I'm comparing the parameters.
Why doesn't this allow me to select? Okay, I'm just gonna write that again. So it's c t raised to 1 upon 2. So what we have here is c integration from 0 till infinity, t raised to 1 upon gamma, e raised to minus ct dt, right? Okay. So now, yes, go on, Vanshita.
So we are not including the, I'm just including the like the variable parameters, not the constants, because we can multiply and divide that, right? So
Yeah.
according to the PDF, while comparing, we have e raised to minus lambda x. So we can say that lambda will be equal to c. And the power of x over here is alpha minus 1. So we can say that alpha would be 1 upon gamma plus 1.
Very good. And so what should I be doing now here? To compensate and, make it a whole f of x with lambda such and alpha such and so and so.
So we would have to divide by c raised to 1 by gamma plus 1. And multiply by, multiply and divide as in the constants that are there.
Yeah. So let us try to, first of all, write the f of x for these guys. So we'll know what do we want. So instead of lambda, I'll have C. So C raised to alpha. Alpha is 1 upon gamma plus 1. And I want the gamma of 1 upon gamma plus 1. And instead of x, I have a t here. So I just write t raised to 1 upon gamma. Plus 1 minus 1 cancels out each other. And I have e raised to minus of cx. Because that is my lambda, right? So, if you always, try to write what exactly you want, then that will help you to devise whatever should be done here easily. So now what should I be
doing? It would be e raised to minus ct.
Oh yeah, thank you very much. E raised to minus ct. Perfect. And this will be f of t, right? Not f of x anymore. So yeah. This is actually a very common mistake I have seen students doing in the exam time as well, or in the mocks. What they do is, if in the question I've never mentioned about x, the random variable that I'm trying to use is u, and you write all of the function in u, but here you write f of x, because we are used to writing any PDF as f of x. So just be aware of these mistakes. I mean, when you're in the class, you're not under the time pressure, you don't make such mistakes. But when you are under the exam situation, these are the mistakes that can easily overtake the emotion of taking the exam. So yeah. What should I be doing here? Come on, fast.
We'll take the reciprocal of the constants outside.
Yeah, so I'll have gamma of 1 upon gamma plus 1 upon c is to 1 upon gamma plus 1. Perfect. And integration from 0 till infinity. Oh, so again, okay, so we sort of didn't discuss what will happen to the integrals here while we were trying to, substitute these guys. So again, you have to remember, at least in this case, the integrals do not change, but sometimes these might change. So we know that for x equal to 0 and x equal to infinity, we have this integral where x is changing. But now when we redefined it, we know we are changing with respect to t. So what you have to do is take care of limits of the integral. So I have this is my lower limit and this is my upper limit, right? So you write subsequent values for the t. So let's say if you get x value 0, what will your t be? 0, right? And if my x is infinity, what will my t be? Infinity, which is why you have these limits 0 to infinity. So let me just maybe put a marker over there, that these 0 to infinity that you have are these 0 to infinity, not these 0 to infinity which you previously had over there. So these 0 to infinity are these 0 to infinity. So again, this is a very crucial step. So again, here we have 0 to infinity as it is. Here we aren't going through that step, but yeah. So again, I should just write here f of t, right? Because I'll get this as it is. This is same, and even this is the same. So dt, and what should this be equal to? Anyone?
1, ma'am.
1. Perfect. So I'll just have to now simplify this expression right here. So I have c multiplied by something like this, and then you divide it, and so I have a c here and I have a something else here. So actually what I can do is I can just ignore this c from here and I can take it downwards. So plus 1, and this c will come here as minus 1. So it will eventually cancel each other out. And what you're left with is this. And that itself here is your mean of Weibull distributions. Is this clear to everyone?
Yes.
Anvaya? Isha?
Yes.
And I guess Mihir and Savri, both of you guys did using gamma function instead of gamma distribution. So it really doesn't matter what you take into consideration. I think it was just easy because you have gamma distribution right there. I mean, gamma function also comes in the table booklet even prior to gamma distribution, but it really doesn't matter much. So, okay, that was it. But again, let us take something else for homework now. So this was a very hefty derivation that we just did and go through. So I want you all to try to figure out expectation of x squared for Weibull and then subsequently variance of x for Weibull. Can this be expected of each one of you?
Yes, ma'am.
Yes.
I mean, not tomorrow, not tomorrow. You can do it at your convenience because I do understand you guys must be having classes in the morning itself. So yeah, don't worry about this homework, but I want this at least in like 3 or 4 days. So yeah, that's it. And what about a Burr distribution? Was anyone able to derive the mean of Burr distribution? Anyone? So actually, it is really not possible with the techniques that we have yet learned to figure out the mean of Burr distribution manually. So it just cannot, be derived. So that was just something that I wanted to give you guys as a test or something. Like maybe if someone could have derived it, even I would have learned how to derive it. But yeah, again, don't worry if you didn't get the Burr distributions mean because there is no possible means to derive it manually. And what you can do is instead just open up your formula booklets, and on page number 15 you have a formula for the mean of Burr distribution. Can someone dictate that to me?
It's gamma of alpha minus 1 upon gamma into gamma of 1 plus 1 upon gamma into lambda raised to 1 by gamma upon gamma of alpha.
Okay, so this is my mean of Burr distribution. And do you guys remember what were we supposed to compare this with?
Pareto.
Right? Compare with which Pareto? So we were supposed to compare this thing with the Pareto distribution, which was like, I guess it was 2-parameter Pareto distribution, where gamma's value is 1. Let me just check once. Yeah. So it was Pareto with 2 variables, alpha and lambda, where gamma is 1. So can you guys give me the mean of this Pareto? So essentially we'll have something to compare it with.
Lambda upon alpha minus 1.
Exactly, lambda upon alpha minus 1. So we know that if we try to substitute gamma equal to 1 in here, we should have this as the answer. So I hope you guys can do that now. I mean, not deriving this, but just substituting gamma as 1. And then you should get this as your answer. So again, take that as a homework, I would say. Yeah, someone wanted to say something?
That part is doable. Just the expected value of x part was a little...
Yeah. You actually don't have to derive that because so like when I studied this subject, even I tried a lot to derive Burr distribution. I think I spent like 2 or 3 days and I was just trying to compare this with a lot of distributions and I just wasn't able to. So I think it was just like a good exercise. But yeah, don't worry about deriving this. So we have to figure out my expectation of x of Burr when gamma takes the value 1, right? Oops, so sorry here, I shouldn't even be writing this. Yeah. Okay, so I'll just, leave that there. So I guess that's it. So does anyone have any questions in regards to all that we have studied so far? So right from the starting, we did a sum, Poisson and exponential distributions difference. And then we had a look at, let us go through each one of those slides. Then we had a look at memoryless property, right? So we studied what happens in memoryless property and what essentially how does it help us to derive the things that we care about easily. Okay. And then we studied about MGF, which is moment generating function. And we also had a look at why do MGFs matter and why do we even need MGFs. And then we had a look at gamma distribution again. We studied the importance of gamma function. And then we had a look at MGF of normal 0, 1. So again, here we used the technique of completing the square, where instead of trying to solve this integral, we tried to complete this square and compare this with another normal distribution which had mean t and variance 1. So that is how we evaluated the MGF of normal 0, 1. And then we had a look at log normal distribution. And after which we had to look at its moment, which will help us to define the distribution. So again, whenever we are trying to, summarize a distribution, we don't want to write the whole, we don't care about the whole f of x and all those stuff. Sometimes the art lies in, leaving the rest of it and just having what's essential. So we capture everything in the moments. And then we had to look at Pareto distribution and then generalized Pareto distribution. And again, here we tried to use the technique of, not having to solve the integral, but just comparing this with another Pareto distribution with some parameters being put accordingly. And then we looked at the Burr distribution, and I guess, so it was try the mean of Burr distribution. So I guess it was just enough to try because I knew that you guys will not be able to solve it anytime. So again, and this showing is, I guess, just easy. And then we have Weibull distribution, which is really good because it provides you a lot of flexibility depending upon the value of the gamma that you can have. And again, in terms of loss distributions, we care about, the higher chance of incurring a higher loss, not a lower chance of incurring a higher loss. So we generally care about this case a lot more than this case. So again, because we're looking at losses. If we were looking at profits, then we would obviously have cared, about profit having a lower chance of occurring. But because we're looking at the losses, which are claims, we know that we have to care about the higher chance of a higher loss incurring, because that is what we don't want to happen. And that is what we want to hedge against or reserve against. And then we did some power comparison and we did the mean of Weibull distribution. Okay, and then we know that, we studied some techniques of how we can compare this data that we have at hand and try to model it using some distributions, theoretical distributions, which we have yet studied. So the first one was method of moments, and then we looked at method of maximum likelihood. And it's very important to know the difference between probability and likelihood. And they kind of are interchangeable, but there is this subtle difference that lies from what do we know about and what are we trying to care about. So I guess that was it. And then we looked at, the whole process of log likelihood and then some example. And I guess this we just revised today. So yeah. And we just solved for each of these things. So let me just save this because that is the end of our chapters. And I don't know. Yeah. So I'll just save this and now we'll start with next. Oh, again. So does anyone have any doubts with this chapter?
Ma'am, I just wanted to ask, what does degrees of freedom mean exactly? I mean, when we say X follows some degrees of freedom, what does that mean? I mean,
Okay. Let me try to explain that to you. Maybe we'll add some slide here. Okay, I'm just gonna go. I didn't remember how to add a slide next to that. So yeah, I'm just gonna go here and I'll take here. So let us try to understand what exactly degrees of freedom mean. So let us take a very, very simple example. I have 2x plus 3y and that is equal to 12. Okay. So what do you guys think is the degrees of freedom here in this expression, right? Here, in this equation. How many degrees of freedom do I have? Anyone? How many degrees of freedom do I have? Or is this a very unusual thing where you might not have imagined that there do exist degrees of freedom here? So again, try to recall what does degrees of freedom mean. So for those of you, who have, I know that all of you have some idea what degrees of freedom are. So try to recall all that you know yet about it and try to see what kind of degrees of freedom do you see here. So again, just let me break the ice. And what I'm trying to say here is, when I'm saying how many degrees of freedom do I have here, what I mean is, how many variables can I vary at a single point in time? So let us try to write all the values of x and y that this expression can take. So I have my x value here. So if I say that my x takes 0, what should my y be? Anyone?
4.
4. If my x is 1, so again, I'm looking for integer solutions, not in terms of decimals. Okay. So what should I write here next? If my x is 2, what do I get here? Nothing.
It won't be integer.
Right. So let us put our y as 0. What do I get my x as?
6.
6. And so on basically. So if I put this as 4, so basically, see, what I'm trying to do is I have to divide at the end by 2. So I know that whenever I'm multiplying 3 with any number and subtracting it from 12, it has to be an even number. And this is an even number itself. So I know that all of my even numbers, even multiples of 3s, will be the ones that I have to look at. So 3, 6, 9, 12. And this is like 1, 2, 3, 4, right? So now I can take my y value as 2 And what do I get here? 3. So yeah, that's good. So do you guys see what's happening here in terms of degrees of freedom? What did we just do? So
We
let
can
us start with
vary only one of the variables. The other one has to adjust.
exactly right. We can only vary one of the variables at one single point in time. So if I give you that I am taking my value of x as 6, you cannot choose by your own what your value of y can be, right? It is dictated by the equation which it has to satisfy. So the number of degrees of freedom you have here is 1. So that's it. This is all you need to know about degrees of freedom. So the number of degrees of freedom you have here is 1. Does this make it a bit clearer?
Yes, ma'am. Yes, thank you.
Okay, perfect. I can actually sense the happiness in your voice. Okay. Anything else anyone would like to ask or clarify? So that's it. Let me just save it and we'll start again. Yeah. Can you all see? Maybe, I guess you are seeing something else. Huh? Can you guys? Yeah, something. Perfect. Okay, so that was our first chapter, loss distributions, that we just finished off with. So we're starting off with our next chapter, which is called reinsurance. Does anyone know what reinsurance means?
Ma'am, it's insurance of the insurance companies.
Exactly. What about others? What do you guys think reinsurance is?
Same what Anvaya said.
Just try to say it again in your words.
Insurance companies have insurance for beyond certain limit of amount, so that's for the insurance.
Yes, that's correct. What about others? Come on, I want to hear it from everyone.
In case the company incurs multiple claims of very large amounts, then as a backup.
Yeah, backup is a good word. Again, Mihir, you want to say something?
Insurance company goes to reinsurance companies so that they can protect them against huge losses.
Yeah, that's true. And how do they protect them against huge losses?
They fix a if the claim amount is something above a certain range, then the reinsurance company has to pay it for them.
Okay, so this is just one possible kind of reinsurance treaty that they can have. Very good. What about others? Andrea, have you spoken yet?
Yes, ma'am. I mean, I was the
Okay,
one who
then, okay, yeah, then I guess it was Savri, right? Savri, what do you think?
Ma'am, yeah, the insurance that the insurance company takes, like, is the same that Neil said, or if it incurs some huge loss, so for that loss.
Yeah, so basically, in short, it is just the insurance purchased by the insurance company itself, right? So whenever I, as a customer, go to any insurance company and try to insure against maybe my car, my house, or burglary or something else, I know that in a way I'm scared that this event might happen and it might give me a huge financial loss wherein I would be financially devastated, and that is why I want to insure against it to save me from such a huge loss incurring, which I think has a good chance of happening, and that is the reason I take insurance as a safety net for that, right? So the same thing happens with the insurance company itself. They are worried that many people will claim at the same time for a lot of amount that they might not have in their reserves. So what they do is they try to insure the claims that they can incur, so that if there are a lot of and so many claims which goes beyond what they have held in terms of reserves, then the insurance company can chip in and try to help them with these kind of losses. So what happens is they can't just, so as we can't just go to an insurance company right before my house is gonna go let's say devastated by flood, because I already know that the flood is gonna happen. So we already go in advance and try to buy some insurance contract with the company, and that is what the insurance company does. So even before this event happen, they will approach their insurance company and they'll try to have some sort of a contract, some sort of a formal treaty, which will guarantee what is going to happen in such and such circumstances, and everything that will take place will be dictated by the contract that they have signed. Right? So again, whenever, let's say now, if I'm saying that a company has incurred a claim, so again, now we will have to differentiate between these two companies, right? One company will be the company which is providing with the insurance to the customers, to the general public, and the other company will be the company which is providing insurance to the insurance company itself, the reinsurance company. So we'll have these two separate names. Let us say one is seeding company. So when I'm talking about the seeding company, this is the company which is provided direct insurance. And this is the company which provides insurance to the general public. And the next kind of company that we'll have is just called reinsurance company. Okay, so I hope that's clear, and this will help us, to discuss again about what's going to happen next. And the risk, so generally what, let us say that, we're insuring against the claim amounts. So that claim amount which we have incurred against is known as ceded risk. So I can just write it as ceded risk. And this is what we're trying to basically insure against with the reinsurance company, being an insurance company myself. So again, there can be various different kinds of treaties that you can sign with the reinsurance company, if you are the insurance company itself or the ceding company. And we'll have, so this is again, these are the ones who are getting reinsured. So let us try to have a look at different kinds of reinsurance treaties that we can generally have. We don't say it as treaties generally, but yeah, different kinds of reinsurance that we can have. So one kind of reinsurance is proportional reinsurance. Would anyone want to guess what must be happening in here?
Is it something like some portion of the insurance is reinsured and something like that?
So you're saying some portion of insurance
is insured by the reinsurance company, not the entire entire portion.
Yeah, so see, that will be the case always, right? Because if reinsurance company will insure each and everything, then okay again. So again, whenever we are looking at reinsurance aspects, it is not exactly, not exactly something that the customer and the direct insurance company have in general, but something else. So what happens with the reinsurance is, let me tell you guys what happens in non-proportional, and then you might guess, what happens in proportional. So let us say I have the claim amount X. So I'm saying that I have a original claim amount. So I'm saying that my original claim amount is X. Okay. And if I'm talking about non-proportional reinsurance, what happens is the reinsurance company will pay some portion of this original X, but not necessarily. So when I'm talking about non-proportional, basically what's happening is, what this reinsurance company will say is, if at all the ceding company incurs a claim which is higher than a particular amount, let's say M. So M is the limit. So this is generally known as the retention limit. So what this insurance company is saying is कि अगर उस कंपनी को क्लेम आ रहा है जिसका, so if this insurance company is incurring a claim amount which is higher than M, then the reinsurance company will chip in and will pay all the amount after M. So up until M, the claim will be incurred by the ceding company, but then the claim amount which is after M will be incurred by the reinsurance company. So that is how non-proportional insurance works in one of the examples of non-proportional insurance. And again, let me just break it to you guys now. In proportional insurance, what happens is, let us say my original claim amount is X, and the claim amount which ceding company will have to pay. So let us say, so ceding company ka claim amount net will be Y. So net. So whenever I'm talking about net, I mean कि actual में ceding company कितना claim का भरपाई करने वाली है. Okay, so that is net, and this is the gross claim amount, because this is the actual claim amount. So again, I mean original claim amount, gross claim amount, these are interchangeable, so not a big deal over there. But net, again, the same thing is going to happen here as well. So जो ceding company है, the amount of claims that these will have to incur will be some proportion of X. Not all of X, always. So what we saw in non-proportional was only if and only if my claim amount exceeds the limit M, then the reinsurance company will chip in and pay the rest of the money, pay the rest of the claim amount. But here in proportional, what happens is, for each and every claim, my reinsurance company will pay certain amount of that claim. And this C can just be, 0.25. So let's say 0.75. So what's going to happen is that 75% of each and every claim amount will be paid by the ceding company, and 25% of each and every claim amount will be paid by Z, which is the reinsurance company's claim amount.
So in proportional, there is no M limit, like after a certain limit, only the reinsurance company will pay a part or something.
Exactly. So let us say if you incur a loss of 10,000 and it's 0.75 is the C value, then the ceding company will pay only how much? 7,500, right? And the reinsurance company will be paying 25,000. Sorry, 2,500. And let's say if the M limit set here was 50,000, then in terms of non-proportional insurance, who will tell me what should be, the distribution of the claim amount between insurance and reinsurance company? So the X here is 10,000 and my retention limit is 50,000.
Insurance company will pay 10,000.
Insurance company will pay 10,000, that's it, right? Reinsurance company won't even know that such kind of a claim happened, because whenever they're writing this in their books. So see, again, you have to take into consideration that whenever a claim is incurred, the person who is going to, claim will only claim with respect to the insurance company, the direct insurance company, and not with the reinsurance company. So the primary customer and the reinsurance company won't even know each other, and they don't care about the existence of each other. I mean, maybe the customer does, because if the direct insurance company goes bankrupt, then it's a worry for them as well, because they won't be paid the claim amount they were promised to. But yeah, again, so they are not directly in touch with one another. This direct insurance company, ceding company, acts as an intermediary between those. And now what's happening is, whenever you incur a claim, you record it with the insurance company, they have it in their books, and they'll see if it exceeds M or not. And if it exceeds M, they will record this in the reinsurance company's books. And that is how they'll come to know, that this thing has exceeded M, and will have to, incur some part of the claim that the ceding company has incurred. Does this make sense?
Yes.
So again, we have to look at, everything in the contract. So now reinsurance company is providing this ceding company with insurance against the claims, right? So what do they get in return? Can anyone guess? So we as customers, we pay premium monthly, right, to the insurance company. What would reinsurance companies be getting?
Same premium is divided between the two companies, right?
Exactly. So it can and cannot be the case again. So it depends on what kind of a contract they have. I mean, it could include, as he just rightly said, some proportion of the premium that these companies have received initially might be transferred to the reinsurance company, or it might be, some certain amount, or it could be something else as well. I mean, depending on how they form the contract and what suits their purpose the best. So again, the insurance company, the ceding company will be paying premium to the reinsurance company in exchange of the insurance that they provide to these guys for larger claims and for basically any sort of claim. And I guess that's it about, the theory of reinsurance. And again, we can divide the kind of reinsurances that we just studied into two subcategories further. So whenever I'm talking about proportional reinsurance, I can again have two subcategories of reinsurance. So what happens is, whenever I'm looking at this, let me just maybe take a new page. So if I'm looking at proportional reinsurance, I can again have two subcategories of it. One is known as quota share. These days I think whenever I say quota, it just reminds me of KOTA quota. But yeah, I guess, I don't know. Quota share, and then the next up you have surplus. Is anyone here from the engineering background? Or did anyone study for the entrance exams? No one? Me neither. High five to everyone. Okay, so let us try to see what happens in quota share. So whenever I'm talking about proportional reinsurance, we know that we have something X initially, and Y is just some proportion. So yeah, Y is basically just some proportion of X, and Z is again some proportion of X. So did you guys see something here, whenever I'm writing y as cx and z as 1 minus c of x, I'm making sure that my y and z, if added, sum up to x, right? Because each and every bit of the claim amount has to be either incurred by the insurance company, the direct insurance company, or the reinsurance company. So this is the claim that I have, and this is with the reinsurer. And this is with the ceding company. Yeah, so whenever I'm talking about something like quota share, we have the same thing, y is equal to cx. This is what exactly happens. And whenever I'm talking about surplus, what happens is the proportions can vary. So for certain kind of claims, they might say that, C is 0.25. And for other kind of claims, they might say that C is just, let's say 0.1 or something else. So what happens is, let's say we have various kinds of insurances coming in or claims coming in, motor insurance claims and car accident insurance claims. So they can have a varying C for each different types of policies that the claim can incur on. So if that is the case, in terms of proportional reinsurance, it is claimed as surplus reinsurance. And if we have a single C, which corresponds to all the claims that you can have, we'll call it quota share. And in terms of what we will be studying in this chapter at least, is quota share. So we'll have a look at quota share, because again, whenever you're looking at surplus, with all of these C's being different, it is kind of complicated to do it manually. I mean, not that complicated even. But again, it's just, doing all of these individually again and again for the separate and different C's for separate policies, and then just kind of adding them up or something else. So again, in terms of quota share, what happens is y is cx and my z is 1 minus cx. And there are certain names given to these things. So the portion of the risk that is with the reinsurer, so basically Z is known as ceded risk. And the thing that you have here is the retention. So this is how much the direct insurance company has retained with themselves. So it is known as retention. Again, these are just names that is, I mean, even if you don't know it, it's fine. But again, it's just good to, know the terminologies of what you're trying to study. So here, again, now next up, you have non-proportional kind of reinsurance. How do you guys think there can be different ways of non-proportional kind of reinsurance? What different ways do you think, can there be of non-proportional reinsurance?
Ma'am, can you please explain the surplus part again in short?
Okay, yeah, sure. Yeah, so basically, let us say I have an insurance company of my own, and I look at motor claims, I look at accident claims. So these are the two kinds of claims that I look at, and I'm trying to hedge my risk. So I go to an insurance company and I sign a treaty with them that I will retain 75% of all the claims that I have. So what is my C here?
0.75.
0.75, right? And that is how it works in quota share. And what will happen in surplus is, so let us say I now again go and try to have some sort of a treaty with the reinsurance company, and I see them that if I incur a motor claim, I'll keep 75% of it, and if I incur an accident claim, I'll want to keep 90% of it. So you are basically trying to have different amount of C's for different kinds of claims that you can incur or different kinds of policies that you might have. So here I was looking at the claims. So it can differ, the C value can differ basically. So
Yeah,
if that is
got
the
it.
case, then
According to the
yeah,
policy, the type of policy, the C will change.
the C will change, exactly. So that's it. And it's like not much different than quota share, I would say, because it's just individual quota share is different. But yeah, so next up we have non-proportional reinsurance. And again, we have two different subcategories within the non-proportional kind of reinsurance. The one that we're going to study in this chapter is known as individual excess of loss. So you can have an E as well here, but I'm just writing it X because that is how it is categorized, XOL generally. And the another kind of non-proportional reinsurance that you can have is known as, so again, see, here we have in the name itself, individual excess of loss reinsurance. And the next up we'll have stop loss reinsurance. So the names are a bit confusing because, the names don't, they do represent what's in there, but it's just not that convenient, I would say. So again, if I'm trying to explain you guys individual excess of loss, so what happens here is what we just saw previously in this slide here. So what will happen is in individual excess of loss, I'll have the insurer company. So insurer will, set a retention level, which is M again. So I know that my M, which will be greater than 0, of course, otherwise, it wouldn't make any sense. And what happens is the ceding company will pay the full total of the claims, which have the value of X less than or equal to M up to some upper limit. So the company can actually, say that, I'll pay the claims only from M to 2M. So what does that mean? So let me just maybe try to draw a line, and this is 0 and this is M and then this is 2M. So what the reinsurance company will say is, I will pay all the claim amount that is incurred from this M till the 2M. So if let's say we have a claim, if let's say we incur a claim, which is somewhere here, then the reinsurance company will play no part and the insurance company will pay all of this amount. But if the claim amount is somewhere here, then the insurance company will only pay this much and the rest of it will be met by the reinsurance company. But if the actual claim lies somewhere here, what will happen is this much part of it will be paid by the insurance company. The rest of it will be paid by the reinsurance company. And the one that lies again up above the limit 2M will be paid by the insurance company again. So what's happening here in individual excess of losses? They're just giving you a particular limit up to which they will incur the losses from each of the claims that are incurred. And if it doesn't go beyond that limit, then there's no role that they play. So again, if I were to write the distribution of, let's say, Y, so maybe we can do that later. So I'll just do that later. Okay. So let us see what's, or maybe just do that now. So we have Y. Okay. So I'm looking at Y. And my Y here is the portion that the ceding company will incur. So what do you guys think will happen? So I know if my claim amount, actual claim amount is less than or equal to M, and if this is greater than M. So these are the two kind of possible scenarios that I can have here. So I'm ignoring the case where you have this 2M. Basically, it's just infinity, that's it. So for anything which is above and beyond M, the reinsurance company will chip in and pay the amount. So what do you guys think I should be writing here? Anyone?
For x less than m, it will be x, right?
It will be X, yes. Because if my X is less than M, whatever the claim amount is, that is being fully paid by only the ceding company. Very good. And what if my X is greater than M?
X minus m.
X minus M. And why do you think it should be X minus M?
Oh no, it's not. No, it won't be x minus m. Just a second. It will be m. Sorry, it will be m.
And why do you think it should be M?
Because above m, it will be paid by reinsurance, right?
Yeah. Does everyone else agree with what just Savri said?
Yes. Yes.
What about others?
Yes, ma'am.
Do you guys see why is it the way it is? Right? So it is either X or M, depending on if my X value is less than or equal to M or greater than. So again, instead of, just writing this whole a big distribution, I can also summarize this thing, right, as, just minimum of X and M. So if
But
my
then,
X is less than M,
ma'am, what about the part that needs to be paid beyond 2M?
yeah, so actually I was trying to, move this diagram from here because what I'm concerning myself here, I'm saying that for all M greater than 0, anything beyond M, so anything greater than M, paid by reinsurance company. And that is the case that we had a look at. So I'm not considering this 2M here right now, but again, we'll have a look at, what happens if we have 2M here. Okay, maybe let us try to have a look at that right now itself. So let us try to see what will happen to our Y if I have a case like this. So again, the kind of things that I have to look at now are X less than or equal to M. What should I write here?
X. Oh, sorry. I thought you were asking about the number associated with
Yeah.
X less than.
Yeah, fine. What should I be writing here? What are the conditions that I will have now?
X lies between M and 2M.
X lies between M and 2M. Exactly. And what should be here?
Greater than 2M.
Exactly. And what should be my values here?
Between M and 2M, it will be M, right?
Yep, that is exactly correct. What about this case?
M plus X minus 2M.
M plus X minus 2M. This is absolutely correct, Isha. Very good.
This will be
Does everyone
minus
see?
M.
So it will be X minus M. That's it, right? Very good. And why did you take M plus X minus 2M, Isha? Can you explain that to everyone?
So it will be 0 to M for the first part. Then M to 2M will be paid by the reinsurance company. That is 2M minus M, that amount. So
Yeah.
it becomes M only. And then whatever is further ahead of 2M, that will be paid by us. So that will again be X minus 2M. That is the balance amount.
Exactly. So
M plus X minus 2M, the two parts that are paid by us.
Yeah. So basically, we can also say that it should just be x minus 2m minus m, because whatever the amount is above and beyond, we know that only this difference is being paid by the reinsurance company, which is 2m minus m. So it accounts for all of this. I mean, this is the bracket that we just subtracted right there, and 2m minus m is just m, so it's x minus m. That's it. Is this clear to everyone? Does this make sense?
Yes, ma'am.
Perfect. And I hope it makes sense to everyone else as well. So again, just to remind ourselves, this will be the net claim amount for the ceding company and the Z. So let us try to again, have a corresponding distribution. So again, forget about this. We are looking at this right here, and let us try to have the distribution for the reinsurance company. What do you guys think will that be here? So again, we'll have two different cases, x less than or equal to m and x being greater than m. So what do you guys think it will look like for the reinsurance company?
For the first part, it will be 0, and for the second part, it will be x minus m.
Does everyone agree with that?
Yes.
Yes.
And it makes sense, right? Okay. So let us try to see what happens here. So for this case, I'm trying to look at Z. And again, I'll have three cases, x less than or equal to m, and x to m, and x being greater than 2m. So what do you think is going to happen with the reinsurance company here?
Zero, x minus m, and then m.
0, and this will be yeah. And what will we have here?
M.
M, exactly right. And this m is what? Just 2m minus m. So that is how you have derived it. Easy, right? And again, this is all that there is in this chapter, and the rest of it is actually very simple. You just have to take expectation, figure out some moments and see what's going to happen and blah, blah, blah. So figure out some distribution. And there is just one more thing that's there in the chapter, which is, finding the distribution of the claims for the reinsurance company, which we'll have a look at in some time for sure. So again, I think that was it about individual excess of loss. So we didn't really have a look at yeah. So we didn't really have a look at, stop loss insurance. So yeah, we only had a look at this. And let us now try to see what's going to happen if we have a stop loss reinsurance. Has anyone heard about stop loss reinsurance? No. Okay. So actually it's not much different, but what happens is in stop loss reinsurance, so again, it is actually similar to the way we subcategorize proportional reinsurance. So in stop loss reinsurance, what will happen is you won't go and, decide the reinsurer's claim for each and every single policy that you have. So you'll group a bunch of policies together, and then you will see if that certain amount, if that certain sum exceeds a particular value, which is the retention value, which is being already set by the treaty in place, and if that exceeds, the reinsurance company will chip in and pay the rest of the amount. That's it. Does this make sense? So what I said was, instead of having only one policy, which is let's say A, and then we see, if the claim amount from that one policy A, does it exceed M or not? So instead of asking that question, what now we will do is, we'll bunch a group of policies together, let's say A plus B plus C, and we will see if A plus B plus C exceeds a certain value, and if it does, that will be paid by the reinsurance company. Does this make sense?
Yes.
Yeah. So generally what you can say is, the kind of premium that happens in this case can also be, so see, there can be various conditions. So हम जो कहते हैं ना शर्त लगाना, or some conditions that we have कि अगर ऐसा होगा तो हम ऐसा कर देंगे, ऐसा होगा तो हम ऐसा करेंगे. So that is the kind of things that even these companies are doing when they're writing contracts with each other. So they can also, state certain claims that, let's say, the kind of reinsurance that they might have is that if they receive the claim amount, the total claim amount from a bunch of policies, which is higher than the 105% of the premium that they have received from those particular policies, then the reinsurance company will pay, certain amount. So that is how they can work. So it can pay, the 90% of the excess, and it can pay the 100% of the excess, which was what we had a look at. So right now what we said was, if the claim amount exceeds M, the 100% of the claim amount, which has exceeded the value of M, will be incurred by the reinsurance company. So it can also be the case that not all of that is incurred by reinsurance. So they can again say that, कि 2M minus M का जो आधा है basically M, they won't incur all of it. They might just say that we'll incur 90% of it. So 10% of it can still lie with the insurance company. That's not a big deal. But these are just certain kinds of, different kinds of treaties that these guys can have amongst each other. And that's basically just, so the crux is about finding what will be the distribution for Y, the ceding company, and how will the distribution for the reinsurance company look like. And that's it. That is all that there is to this. Maybe let me just circle this. And yeah. So I hope you guys will remember that we looked at, maybe I can just, yeah. Everything is about excess of loss. Nothing about stop loss reinsurance. And we don't care about stop loss reinsurance in this chapter itself, and neither in the subject. So yeah, and again, there is one more difference between these. So in stop loss reinsurance, there is no limit, so the kind of stuff that's going to happen can be basically unlimited. And it's, again, it just depends on the treaties that these guys have and the rest of it. Okay, so let's go to proportional reinsurance. So the distribution I have for Y and Z is pretty much clear here. So if I were to, just graph these policies. So let's say I'm trying to graph these policies. And would anyone want to guess what will I have on the x-axis? So that will be the claim amount, X. And this will be the number of claims that I've incurred for that one particular thing. So let's say I have some graphs here. Okay, so what will happen is the reinsurance company will pay a certain proportion of each of this claim, right? So I can just, shade some portion of each and every claim that I have incurred. right there. And that will be the portion which is incurred by the reinsurance company. And the rest of it will all be, incurred by the insurance company itself. Does this make sense?
Yes.
And if I were to draw this individual excess of loss, what will happen is something like this. So let's say I have again some. Okay, so this is how my graph is. Let's say this is X and this is again the frequency. And let's say my M is right here and my 2M lies somewhere here. And the company, the reinsurance company basically says that I'll pay for, everything which exceeds the value of M, but it has also to be lower than 2M. So I'm not going to pay something which is higher than 2M. So what will happen? The insurance company will be paying this, and they'll also have to pay this and some bit of there. So that is what the insurance company will be paying. And for the reinsurance company, it will be this part, and this part right there. Does this make sense? So yeah, that is basically that is basically the crux of this chapter. And the next step we will study, how to derive, maybe, let's say even before we do that, let us try to derive the expectation and variance for the proportional kind of reinsurance. So again, so from this onward, whenever I say proportional, I'm actually referring to the quota share kind of proportional reinsurance. And whenever I say non-proportional, I'm referring to the excess of loss kind of non-proportional reinsurance. So let us try to have a look at the proportional reinsurance. What happens in that case? So we know that from X, we know it can be Y and Z, where Y is just some proportion of X and Z is some another proportion of X. So if I were to write expectation of Y, so basically expected claim amount that my insurance company has, what will that be? Anyone? How can I write my expectation of Y?
C into expected value of X.
Exactly. It will just be X. So I will replace my Y with CX, and C being a constant will just come out, and it will be expectation of X here. And for expectation of Z, what will I have? Expectation of 1 minus C times X. And this again being just a constant will come outside. So again, we can, from both of these, we can conclude that my expectation of X is equal to expectation of Y plus expectation of Z, right? Is this true? Can I write that my expectation of X is also equal to expectation of Y plus expectation of Z?
Yes, ma'am.
Yes. So, okay, that's it. And let us now try to figure out this variance. Let's see what happens with the variance. So if I were to figure out the variance of Y, what will that be?
C square expected value of X.
C square expected value of X, variance of X.
Variance of.
Yeah, because we're trying to, yeah. Actually, that was the same mistake, which I did when I was teaching this subject previously. I wrote C square expectation of X. That's, yeah, it's no worries. So let us see if we are trying to figure out the variance of Z. What will this be? How will I write my variance of Z?
1 minus c square variance of x.
So 1 minus c the whole square variance of x. So now can I say whether my variance of x is equal to variance of y plus variance of z? Can I say this or not?
No,
Why do you think?
because the square factor comes into play.
Exactly. So again, if we look at it in terms of, mathematics, we know that we have 1 minus c the whole square here, and here we only have c square. So the 2c with term will be left out, and it won't certainly, add up. So that's it. And what about other, like, why is expectation equal and not the variance equal?
Because in addition of variance, there is some covariance term also there.
Covariance term. Are we adding two different random variables? So let us try to, sum up these. So let us say I have variance of y is what? C square variance of x plus 1 minus c square variance of x. Where do I have the covariance term here? Give me a minute, guys, okay? I'll just come back. Oh, so till then you guys try to, figure out what's going to happen and why is the variance not equal. So you guys can have a discussion amongst yourself. Yeah, so I'll just come in a minute. Did you guys figure out anything? Was there any discussion happening?
Ma'am, if we expand 1 minus c the whole square, then like even if we try to subtract anything, the c square term also becomes positive when you expand the bracket, right? So nothing gets cancelled
Oh
out.
yeah, exactly. Exactly. I think I missed out on that part. So yeah, 2c plus c square it will be, and variance of x. So nothing's gonna cancel basically. Yeah, that's sad, right? So again, that is just, mathematically why the variances aren't equal. But why do you think logically that the sum of variance doesn't add up to the variance of the actual claim amount? So why do you think I cannot,
Ma'am, is it because the variables are dependent?
variables are different? Is that what you said?
Dependent. They're dependent
Variables
on
are
each other.
dependent. Yes, they are dependent on each other, exactly. And can you explain that a bit more?
Like if according to y, z changes and vice versa. Like so, if we expand the variance of x plus variance of y plus z term, there will be a covariance term.
So okay. Whenever I guess someone else tried to say covariance thingy prior. So I guess what we are trying to do here is this, expand this thing. So you substitute instead of x, you write y plus z. And then you're trying to figure out, right, variance of y plus variance of z. And there will be covariance, 2 times covariance of y and z, right? And this thing will not be equal to 0. Again, yes, that is absolutely the reason why. And that is again, mathematically explaining this. So what's the logic behind it? I mean, what is it that it is true for expectation but not for variance? Like, what is expectation trying to say and what is variance trying to explain? And try to, see on that logic. So without any, I mean, not without any math, but without, I'm not looking for some mathematical explanation, but a logical explanation as to why expectations add up, but not the variance. And why are we left with a covariance term? One reason is, yes, they are dependent. And I think that's a very good reason. I don't know why I'm unable to select this. Should be able to. No, it doesn't allow me to select. I don't know. Okay, let's leave it at that. So again, let me just try to show you guys something else. So whenever I'm talking about mean, I'm talking about, a particular claim amount number that I might have incurred, right? So whenever I'm looking at the mean of some claim amount and I distribute it, somewhere between a reinsurance company and somewhere with the insurance company, I know that all of the claim amount has to be incurred by someone or the other, right? So some portion of it, some part of it, wait, what kind of, we're looking at proportional, right? Okay, so again, mind the kind of words I'm using. Whenever I'm talking about proportional reinsurance, I'll use words like proportion. And if I'm talking about non-proportional reinsurance, I'll use the word portion. So there is a subtle difference, I mean, a whole lot of difference between proportional and portion. So again, whenever I'm talking about the mean, I know that a certain proportion of the claim amount is incurred by the direct insurer and the rest of it by the reinsurance company, right? Can I say that thing for the variance? Like, let's say if I'm looking at the mean claim amount, I know that the mean claim amount, if at all, I can divide it between the insurance and reinsurance company and there will be none left to cater to anyone else. And can I do that thing with the variance? I mean, does it even make sense to add up the variance? Leave apart the fact that they don't add up to variance of X. But does it even make sense to add variance of Y and variance of Z? What do you guys think? Okay, so let me break it to it. Does not, make any sense to add up these variances. So again, so let me just, maybe draw some graphs and it can be a bit clearer. So let us say my claims distribution is this. So this right here is my claim distribution. Okay, and which is X, right? So I have again X right here. So again, X is the claim distribution and this here right is the random variable which is equal to X. So I have the free number of claims. So when I'm looking, let's say I divide can you guys see the screen now? I think I lost you guys for a while.
Yes, ma'am, we can see it.
Yeah, so what I'm plotting here is the distribution of my claim amount, the gross claim amount. Okay, and now I'll just try to again have two different sets of graphs. One can be for the insurance company, basically Y, and the other can be for the reinsurance company, basically Z. And this will again look at the number of claims of those particular amounts. So let's say if I have incurred, so I can just join this, and let's say for 20, where do I go? I go somewhere, no. So let's say it's 25 or 20, okay? Yeah. So let's say I incur 5 number of claims of worth 10,000 and I incur 25 number of claims of worth 20,000. So let me just write it as 10, 20 for now. We can ignore the thousands. Doesn't matter much. So if I'm saying that I'm looking at proportional reinsurance, okay, where let me define my C here. Wait, what is that? Yeah. So if I'm defining this right here, x is again equal to y plus z, and let us say that my y is equals to 0.75 of x, and then subsequently my z will just be 0.25 of x. So my c here is 0.75. Okay, this is the thing that I'm looking at right now. So again, now if I am to plot the same kind of a claim distribution graph, so this was the gross claim distribution, and here now and what I'm planning to plot here is net claim distribution, which is represented by y right there, right? And this will be the reinsurers claim distribution, right? So again, I will just divide it in some subcategories. I'll have some markings here. So I have 10, 20, 30, 40 here. So let me just write 10, 20, 30 here, 10, 20, 30 here. Okay, so we actually don't care, if I am having 2 units as 10 and having 1 unit as 10 here. So what I am gonna now do is try to define this distribution and try to plot it and see how it looks like. So let me have this 5, 10, 15, 20, 5, 10, 15, 20, 25, 25. Okay. So now I had that the claim amounting to 10,000 is incurred 5 times, right? So now hello, am I audible now?
Yes, ma'am.
Yes.
I was just wondering why is no one answering, and then I realized that I'm off. So how far did you guys so just tell me how far were you guys able to hear me? So did you guys was I there in the meeting when I wrote about the C being 0.75?
Yes, ma'am.
Okay. So what I did now was I have just taken my x to be 10. So I want to care about this. So my x is 10, and if my x is 10, I know my y will be 7.5 and my z will be just 2.5, right? So my y is 7.5, I know. And I know that the number of claims that I, as the direct insurance company, will be only 5. So this is my 5, let's say. And right here is my 7, and right here is my 7.5. So if I were to plot something, I will get to a point which is here, right? And for this reinsurance company, I'll have somewhere here 2.5, and we'll have, 5 number of claims, right? And now if I have my X equal to 20, what will be my Y and what will be my Z? Anyone? $16 and $4, right? Am I audible or am I one of them? Hello?
Yes, ma'am, you're audible.
Yeah. Oh, it was 5 and it will be 5 and 15, right? So again, when I'm writing my Y for my X being 20, what I'm doing is multiplying it by 0.75. So it will be 15. And here I'll have 5, right? So I know that my X, which is 20, is incurred 25 times. So for Y, 15 amount will be incurred 25 times. And for Z, 5 amount will be incurred 25 times. So this is 5. And that will be incurred 25 times. And for this guy, Y is 15, which will be incurred 25 times. So now if I try to, plot the distribution, do you see how it varies? So this is gonna look something like this probably, because the reinsurance company only pays a certain percent of all the claims. So even if the actual claim amount is 10, which was incurred 5 times, for the reinsurance company, the claim amount is only 2.5, which is being incurred 5 times, right? So the distribution might look something like this, and this distribution might look something like this. Okay, so there will certainly be the difference in the amounts. But again, let us try to see what happens for each and every claim. So if we look at this claim right here, X equal to 10, I know that I have 7.5 and 2.5 here. So number of claims that are being incurred, let's say 5 times are these, and these are again the claims. So if you add these and if you add this, you will get 10 here, which is something like when you're adding the expectations. But when I'm talking about adding variance, my variance for this is something that I measure here, the dispersion around the mean, right? Here, it would be something like this. And in this case, it would be something like this. So again, it just does not make any sense, at least here, to even add up the variances, because it will just amount to, it is showing you nothing, right? Does this make sense?
Yes.
Does this make some understanding better?
Yes.
Yes, ma'am.
Okay, very good. So again, what we did was we had a look at expectation, we had a look at its variance, and again, we can have a look at its MGF and all those stuff. So let's see if I were to write the MGF of Y. What will that be? How can I write my MGF of Y? So what will be the formula for MGF? Does anyone remember?
Expected value of e raised to t into y.
And then what should I do next?
It will be expected
Substitute.
value of
Anyone can speak. It will be expected value of e raised to
T into CX.
t into cx. And can I write this in any more manner, in any another manner?
It will be MGF of CX.
MGF of x, and it will be TC, right? Not CX. So X is the variable and TC is what I'm taking my MGF parameter to be, right?
Yes, yes.
Does this make sense? Yeah, and for MGF of Z, you can do the same. So it will be e raised to TZ, and that will just be MGF again of X, where the parameter is T times 1 minus C. So that's all for the proportional case. And tomorrow we can have a look at, what happens in the non-proportional case, which is even more interesting given that, you actually have a lot of things at play. And yeah, so I guess that's it for today. Does anyone have any doubts or anything with respect to what we did today? So again, I don't see that you guys might be having any doubts now, or if you have, just ask. Otherwise, what will help is, just to go over it again before tomorrow's lecture. And I think this can be, a bit of